Okay, so let's get into this. You probably don't think much about how we measure length, right? I mean, beyond a tape measure or maybe a ruler from school.
Yeah, exactly. It seems pretty straightforward.
But what if I told you that our entire advanced technological world, things like the tiniest AI chips, even quantum computers, well, they all depend on rulers. But rulers so incredibly precise, they're pushing the absolute limits of physics.
It's quite mind-boggling when you think about the scale. We're talking
Yeah.
about needing to measure things almost down to the atomic level.
Exactly. Imagine measuring the thickness of like a single atom's outer shell. That's the kind of precision we need, and it's what's enabling all this next-gen tech. So today, in this deep dive, we're looking at a really groundbreaking development in how we measure length. Not with a physical ruler, obviously, but using light itself.
Yeah.
And the precision level, well, it just redefines what we thought was possible.
Right. And our sources for this are fascinating.
Mhm.
They're from research detailing this new quantum-level optical frequency comb system. It was developed by the Korea Research Institute of Standards and Science, or KRIS.
That's right, Chris. So our mission today is to sort of unpack what this new system actually is, why it's such a huge leap forward compared to what we've been using, and, what it means for future high-tech stuff.
We'll definitely look at the challenges, the sort of roadblocks and length measurement. The science is called metrology, and how this innovation just kind of sidesteps them.
Okay, let's start with the basics then. Why do we even need this extreme precision? You mentioned the meter. It's not just a stick in Paris anymore, is it?
Huh. No, not for a long time. The actual definition of a meter is based on, well, fundamental constants now, but it's maintained and realized through national length measurement standards. And those rely on incredibly accurate tools.
So these aren't just standard lab instruments we're talking about.
Oh, no, definitely not. Think of them as the gold standard. Top metrology institutes like KRIS we mentioned, or NIST in the US, PTB in Germany, they are the custodians of these national standards.
Right.
And traditionally, they've used interferometers, basically tools that use light waves, how they interfere with each other to measure tiny, tiny distances with extreme precision.
So they're like the ultimate guardians of accuracy for whole countries. But maybe bring it down to earth for us. Why should someone listening care about this super abstract precision? Does it really affect us?
It absolutely does.
Yeah.
It might seem abstract, but it's critical for the future tech that will affect everyone. Dr. Jang Yoon Soo from KRIS put it really well. He basically said that the competitiveness of future industries, think AI, semiconductors, quantum tech, it all hinges on being able to accurately measure and control distances right down at the nanometer scale.
A nanometer.
Yeah.
That's a billionth of a meter, right? Tiny.
Incredibly tiny. And this new system, it's seen as key for Korea, for example, to become a leader in setting these next-generation standards. You simply can't build next-gen computer chips where you're placing components with almost atomic accuracy if your measuring stick isn't good enough.
Okay, that makes sense. So the why is clear, but how are we doing it before this breakthrough? Let's maybe peel back the curtain on the existing methods and where they struggled. You mentioned single wavelength lasers first.
Right. You could picture those like a ruler with incredibly fine markings, but maybe it's only, say, an inch long. They work by using light with a very, very consistent wave pattern. Think perfectly spaced lines.
And that gives them the precision.
Exactly. Nanometer level precision, typically 1 to 10 nanometers. That's phenomenal accuracy.
There's always a but.
But yeah, the ruler is very short, metaphorically speaking.
Mhm.
Because they use just one wavelength or a very narrow range of wavelengths, they can only measure very short distances directly.
So what if you need to measure something longer?
Then you have to stitch multiple measurements together. Move the system, measure again, move it, measure again. It takes time, and it requires incredibly stable mechanics to keep everything perfectly aligned. It introduces limitations in both time and, well, the physical setup.
Ah, okay. So it sounds like a bit of a hassle, especially if you need that nanometer precision over, say, the length of an optical fiber in a quantum setup.
It's been a major bottleneck, yes, a real challenge. Now, the alternative that existed was what we call absolute distance measurement systems.
Okay.
Think of these as the opposite. A very long ruler, but maybe the markings aren't quite as fine.
So less precise.
Generally, yes. They're designed to measure long distances in one shot. Often they work by setting out a pulse of light and timing how long it takes to come back. It's called time of flight.
A bit like radar or sonar, but using light.
Exactly like that. And they have advantages. They're often simpler, more compact, much faster for long ranges. You see them a lot in industrial settings for that reason.
But the precision isn't there for these cutting-edge applications.
Right. Typically, their precision is limited to a few micrometers. My micrometer is 1,000 nanometers, so way too coarse for quantum tech or advanced chip making. The tech just hasn't been good enough to time that light pulse return with the resolution needed for nanometer accuracy.
So basically, for years, you had this trade-off. Super precise, but short and slow, or long and fast, but much less precise. You couldn't really have both.
That's the core problem they were facing. You had to choose.
Okay, so this sets the stage perfectly. We have this fundamental problem. How did the Chris team crack it? What was the magic ingredient, the secret sauce?
Well, the key innovation here revolves around something called an optical frequency comb, an OFC.
Optical frequency comb. Sounds interesting. What is it?
Imagine a light source that doesn't just produce one color or one wavelength, but produces thousands of different colors or frequencies all at once. And crucially, these frequencies are all perfectly discrete, like individual notes, and they're spaced perfectly evenly apart, like the keys on a piano.
Wow, okay. So not just one laser line, but thousands of precise lines simultaneously.
Exactly. That's the beauty of it. Unlike those single wavelength lasers, OFCs have both a very broad range of frequencies, like having a very long ruler, and those frequencies are incredibly precisely defined and spaced, like having superfine markings on that long ruler.
Ah, I think I see where this is going.
Right. It combines both properties. So what the Chris team did, very cleverly, was figure out how to integrate this OFC into a type of measurement system based on spectral interferometry.
Spectral interferometry. Okay, breaking that down.
In simple terms, they use the complex pattern of light created by all those different frequencies interfering with each other. Because the comb's frequencies are so well defined, the resulting interference pattern contains incredibly detailed information about the distance the light traveled. It lets them measure long distances in one go, but with the precision you'd normally associate with those short-range interferometers.
So they essentially gave the long ruler the superfine markings.
That's a great way to put it. They bridge that gap. They combine the precision of really national standard level measurement with the convenience and speed of those absolute long-distance systems.
And the performance figures are just, well, they're kind of stunning. The sources say 0.34 nanometers of precision?
Yes, 0.34 nanometers. That is truly unprecedented for this type of absolute distance measurement over significant ranges. It's among the highest accuracies achieved by any length measurement technology out there.
And it's approaching the theoretical limits.
It's getting remarkably close to what's called the quantum limited precision, the fundamental limit set by the laws of quantum physics itself for this kind of measurement.
Wow. And it's fast, too.
Incredibly fast. Operates at 25 microseconds. So you get the precision and the speed.
And importantly, it's not just some delicate lab setup.
That's another key point. They've apparently designed it to be compact and durable. So it's potentially field-ready. It could actually be used in those high-tech industrial settings, not just in a metrology lab. That offers huge potential for enhancing precision manufacturing, quality control, you name it.
So what are the next steps for them? Are they rolling this out now?
Well, the research team is continuing development. They need to fully evaluate the measurement uncertainty, basically. Put rigorous error bars on that 0.34 nanometer figure and keep refining the performance. But their ultimate aim, it's to establish this system as a next-generation national length standard, to set the new global benchmark.
So this deep dive has really shown how, this quantum level tech isn't just theory anymore. It's fundamentally changing something as basic as measuring distance. It overcomes limits we've bumped up against for ages, that trade-off between being precise and measuring far.
Absolutely. It's not just a small improvement. It feels like a genuine paradigm shift in measurement science. It opens doors to doing things that were simply impossible before because we couldn't measure accurately enough over the needed distances or quickly enough.
Which brings us to that final thought to leave people with. If we can now measure things we couldn't before, things at this almost unimaginable scale with this speed and precision, what does that unlock? What kind of completely new science or new engineering or even everyday tech that we can't even conceive of right now might suddenly become possible?